Okay, in this video I'm going to go through question 1, 2 and 3 of the written section of the test, and I'll post separate videos for the remaining questions. I'll put a link in the bottom, in the description, of the time at which I start going through question 2 and 3, so if you just need to look at one of those, you can jump straight to that. Right, let's get started. So, question 1 says tritium is a naturally occurring isotope of hydrogen. It can be represented as 3,1H. Okay, so just as a wee warning, this mark was an accident. This shouldn't be a mark there. First of all, you should think to yourself, do I know what this symbol means, what it represents? And if the answer is no, then you need to do some more division of your atomic structure. So you need to be thinking, well, what does this 3 represent? What does the 1 represent? And what does the H represent? The H is the symbol for hydrogen, and the 3 and the 1, hopefully you can remember which way round those are. So 3 is the mass number of this particular isotope, and the 1 is the atomic number. I'm using NO dot as an abbreviation for number, so we've got our mass number and our atomic number of this isotope of hydrogen. And question 1a says complete the table to show the number of particles in an atom of tritium. So you've got type of particle, proton, neutron and electron, and the number of particles. So what you've got to remember for this is you've got to remember the definitions for atomic number and mass number. And if you weren't getting this, you need to make sure you do some more revision of the atomic structure topic. Perhaps looking at BBC Bitesize. So the mass number is the protons, number of protons, plus the number of neutrons. Okay, and the atomic number is the same as the number of protons, and in a neutral atom, that's also the same as the number of electrons. Okay, if you didn't know these, you need to make sure you memorise them. Get someone to test you on them. So the number of protons is going to be the same as the atomic number. Well, I knew in this symbol, this is called the nuclide notation, that the atomic number is 1. So if the atomic number is equal to the number of protons, there's 1 proton. The mass number is the protons plus the neutrons, so 1 plus the number of neutrons must be equal to the mass number. Another thing to remember is that to work out the neutrons, you do the mass number take away the atomic number, so 3 take away 1. So the mass number take away the atomic number is the number of neutrons. 3 take away 1, which gives you 2 neutrons. And then the number of electrons, again in a neutral atom, which this is because there's no charge symbol, is the number of electrons is the same as the number of protons, so that's just 1 as well. Okay, and then it says hydrogen has 3 isotopes. So we've got protium with a mass number of 1, deuterium with a mass number of 2, and tritium with a mass number of 3. And it says the relative atomic mass of hydrogen is 1. Which isotope of hydrogen is the most abundant? So in this question, you need to remember the definition of relative atomic mass. Helps to know the definition of isotope as well, but that's not absolutely essential. The relative atomic mass is the average mass of the isotopes of an element. Now, we talked about this quite a lot when we did this topic, but if the average is closer to a particular number, that means there must be more of that number. We talked a lot about the example of if you're in a room full of people and the average height is quite on the small side, that suggests that most of the people in the room are small. So if the average height, if the average mass, if the relative atomic mass of hydrogen is 1, that means there must be more of the isotope with mass number 1. So the answer to that one is protium. Okay, so question 1, I would say it was a reasonably straightforward question on atomic structure, and the main reason I think people might not have gone right with that is either silly mistakes or lack of revision. So like I say, make sure you do some revision if you weren't getting this right. BBC Bitesize is a good place to start. Okay, question 2. So question 2 says Rapid inflation of airbags in cars is caused by the production of nitrogen gas. The graph gives information on the volume of gas produced over 30 microseconds. Okay, so the graph is giving the volume of gas produced over 30 microseconds. So we've got volume in litres on this axis, and we've got the time in microseconds on this axis. Okay, so question A, part I, says calculate the average rate of reaction in litres per microsecond between 2 and 10 microseconds. This is a reasonably difficult question. Most of you went absolutely along the right lines when you were starting this question out. There were quite a few little mistakes, but I think it's something that you can definitely improve on for next time. So again, you might remember the equation for average rate for rate of reaction, or you might need to double check it. So in the data book, rate is change in quantity divided by change in time. So first thing I'm going to do on this question is write that down. So rate equals change in quantity divided by change in time. Remember, the little triangle delta means change in. So we're looking for rate, and we're going to need to be sure about what the change in quantity and the change in time are in order to calculate that. Now, there are different ways to lay your working out for this. I prefer to work them out and then substitute them in, but you can substitute them in directly. So in this one, probably the first thing to think about would be the change in time. So we're going from 2 to 10 microseconds. So the change in time between 2 and 10 would be 10 take away 2, which would be 8. So our change in time is 8 microseconds. Now, change in quantity though is something that we're going to have to work out from the graph. Now, this was where this question was difficult because the graph has got quite an awkward scale. So first of all, I'm going to try and find 2 microseconds. So I've got 5 microseconds here. And so then I've got to work out where 2 is. Well, I do this by just kind of trial and error. So 1, 2, 3. Each little box can't be worth 1 because that wouldn't work out with the scale. So, and halfway must be 2.5 actually, halfway between 0 and 5. So actually each 2 boxes, little boxes, must be worth 1. So we've got 1 here, we've got 2 here, 3. So quite a few of you, there was a little bit of difficulty with reading the graph, but maybe not even, a lot of you worked out where 2 was and then misread the volume at 2 microseconds. So when you're doing graph work, you have to be really careful. Always double check your work for this, because there were quite a few silly mistakes. You'd find out where 2 was, but some people had not correctly followed the line up to work out what the volume was at 2 microseconds. So don't be afraid to draw on the graph. So I'm following the line from 2 up to where it meets the thick line here, which represents the volume over time. And I'm then going to find the exact point at which it meets the line and follow that across. And so at 2 microseconds, I had 10 litres of gas. But I'm looking for the change in quantity between 2 and 10. So at 2 it was 10. And then at 10 microseconds, again, I'm going to follow that line. Don't be afraid to draw on the graph, but if you do draw on the graph, make sure you're nice and careful. So I'm going to follow that line right up to the point at which it meets this thick line here. And then I'm going to follow it across. And again, I'm going to do that carefully. There was at least 1 or 2 mistakes just in following that across. So I've got, now I'm on this scale and I've got between 30 and 40 and I've got 10 little boxes. So I should be able to work out that each little box is 1 and this is coming out at 32. So at 10 microseconds, I had 32 litres of gas. So my change in quantity between 2 and 10, well, I've gone from 10 to 32. So to work out the change, I would do 32 take away 10, which is 22 litres. So my rate is change in quantity divided by change in time. So I'm going to say 22 divided by 8, so 22 litres divided by 8 microseconds. And 22 divided by 8 make sure you use a calculator. Okay, and that works out at 2.75. Now, I can write in my units, and if I'm writing in my units here, I wouldn't expect you to know the abbreviation for microseconds. So there's a couple of things I could do. I could just write them out in full, litres, microsecond, and then I could put to the power of -1 beside my word, because that's the way we've learned to do it. But I could just use the units of the question. I could just write litres per microsecond. Because actually quite often in this case they would give you the units if you're doing a rate calculation. If they don't, they'd probably be a slightly simpler one than microseconds. A lot of you put litres ms to the -1. Now, I haven't taken a mark off for that, but ms is actually the abbreviation for milliseconds, so technically that's wrong. Microseconds actually has this symbol, but you, like I say, you wouldn't be expected to know that. So the safest thing to do if you're unsure of how to abbreviate is just to write the full word. Okay, and then part 2 says, in some types of airbag, sodium azides, NaN3, decomposes to produce sodium metal and nitrogen gas, and it says write a formula equation for this reaction. There is no need to balance the equation or show state symbols. Now, a lot of you got a little bit confused. Decomposition is something we did cover in 3rd year. I would expect you to know the name, but if you weren't sure about what that means, use this as a chance to learn. So decomposing just means breaking down. If something decomposes, generally there's only one reactant, and it's breaking down into 2 different products, 2 or more. So decomposition isn't anything to do with combustion. A lot of you ended up putting oxygen into this equation somewhere. Decomposition is nothing to do with combustion, and there's no need for there to be oxygen involved in this decomposition. So it says sodium azide, NaN3, is decomposing, and it's producing sodium metal and nitrogen. So even if you were unsure about what the reaction was about, you know that the products are going to be sodium metal, Na. Now, a few of you got mixed up with the symbol for sodium. Again, make sure you double check in the data book in the periodic table. Some of you were getting mixed up and putting S for sodium. Okay, and nitrogen. You need to remember that nitrogen's a diatomic, so nitrogen is N2. And then it's the sodium azide that's decomposing, and it gives you the formula for that, NaN3. Okay, so hopefully just by rereading this, that maybe becomes a little bit clearer. So you just need to remember decomposing just means breaking down, and it's not anything to do with combustion, which means adding oxygen. Okay. So question 3. Question 3 says fluorine can form covalent and ionic bonds. Fluorine gas is made up of diatomic molecules. Draw a diagram showing all outer electrons to represent a molecule of F2. So most of you were able to make a decent attempt at this or had some idea of what it was asking, but there were quite a lot of mistakes in this. Again, I think I'm going to put that down to lack of revision, because we did do quite a bit of practice of this, and this is something that should have come up if you revised the bonding topic. Okay, so a diagram showing all outer electrons to represent a molecule of F2. So remember, it's a molecule of F2, so there should be 2 fluorine atoms in the molecule. This is the structural formula for a fluorine molecule. This doesn't show outer electrons. To show outer electrons, what you need to do is you need to be drawing the electron arrangement. So fluorine has 7 outer electrons. So 1, 2, 3, 4, 5, 6, 7. And when it bonds with another fluorine atom, remember it's the the unpaired electron that forms the bond. So I can draw another fluorine atom over here. And I can either represent the electrons with dots or crosses. The main thing I have to be careful of is that the electrons in the shared electrons have to either be within the overlapping area or on the line. So because I've done them on the line on the first one, I'll do them on the line in the second one. So 1, 2, 3, 4, 5, 6, 7. If you feel a little bit rusty with that, I'm going to put a link to a video which will remind you about how to do those electron sharing diagrams. Okay. Part B. Nitrogen trifluoride is a colourless, non-flammable gas with a slightly musty odour. State the name used to describe the shape of a molecule of nitrogen trifluoride. So again, I'm afraid if you didn't get this, it's mainly probably due to lack of revision, or maybe you just got a little bit mixed up. So you should recognise this shape here as a trigonal pyramidal shape. I gave you the mark if you just put pyramidal as well, but the correct name is trigonal pyramidal. Then part C, when fluorine reacts with iron, the ionic compound iron 3 fluoride is formed. And it says, write the formula for iron 3 fluoride. This should be nice and simple. I'm a wee bit disappointed to see a few silly mistakes here, especially with the valency for fluorine. So remember, when we're writing our formulas, we're going to do our crossover method. So we're going to find the symbols for the different elements. Now, iron, you would need to check in the periodic table, but iron has the symbol Fe. Fluorine has the symbol F. Now, we've got Roman numerals in this name. They apply to the iron, so that tells us that iron has a valency of 3. And fluorine, you would need to look at, so fluorine is in group 7, meaning it needs to get one more electron to get a full outer shell, so it has a valency of 1. Crossing our numbers over, where we get Fe, F3. Okay, so again, I might put a wee link to some videos which will help you to just do a little bit more practice of writing formulas if you weren't getting that. Okay, and then finally part D, covalent and ionic compounds have different physical properties. Complete the table by circling the words which correctly describe the properties of the two compounds. So again, this is a bit of sort of like memory work. If you didn't get this, again, you need to do some more revision. So nitrogen trifluoride gas, well, we know that it's a gas, and we know that if it's two non-metals, it must be, or not must, but it's most likely to be covalent. Okay, and if it's a gas, and you've actually seen this already in the question, it's made of molecules, so it's covalent molecular. That's probably the difficult bit about this question actually, is just working out the bonding and structure. So if you're asked about properties, remember, properties link to the bonding and structure, and you need to be able to figure that out. Okay, but it has given you help in the previous parts of the question. So nitrogen trifluoride is covalent molecular, that's the bonding and structure. Iron 3 fluoride is ionic, and it tells you that in the question. That's the bonding, and the structure of an ionic compound is a lattice structure. So once you've figured out the bonding and structure, then you should have learned, or you should have memorised the properties of the different types of compounds. So covalent molecular substances have low melting points. Gases in general, if it's a gas, it must have a low melting point. And covalent molecular substances do not conduct electricity. Okay, our ionic lattices, well, ionic lattices have high melting and boiling points. Now, when it comes to electricity, ionic compounds conduct only when molten or dissolved, but in this question it tells us that it's solid iron 3 fluoride, so solid iron 3 fluoride would not conduct electricity. So that was the correct answer for that table there.